Hi, I'm Tom Bell from Enritsu, and we're here today to do an overview of the new B Series PIM Master, the MW82119B with Site Master option. The system that we're going to demonstrate on today is two 5-meter cables with a PIM standard installed at the end of the first 5-meter cable and a low PIM termination installed at the end of the cable. In this case, the low PIM termination will be simulating the antenna on the system. The first thing we're going to do is do a quick return loss check of the system to see if this is a working system. Standard procedure says that you should always perform your sweep tests first before performing PIM tests. And so looking at this, I have a limit line set at -18 dB and we are passing. So we have a good system to start with. Typically the first test that I'm going to do for verifying cable system performance is to disconnect the antenna from the line and do a distance to fault return loss measurement, which in this case is going to tell me the electrical length of the line. So if I put a marker at the peak, this is showing me a peak at 10 meters. So we're getting a good measurement of the length of the line. While the cable is open, the next logical test to do is go into the measurements menu and perform a cable loss test. I'll do the amplitude to auto scale. In the marker menu, we have an automatic feature to automatically apply markers at the peak and the valley. And so it shows us here that the average cable loss is 3.59, but I've also put markers at the peak and the valley in case someone wants to go and mathematically verify that measurement. The next measurement we're going to do is attaching the precision load to the end of the cable and performing a distance to fault return loss measurement to look at the condition of the individual connectors. And in this case, we'd like to see that the individual cables are below a 25 dB level to show that each individual cable is put together correctly. And in this case, our system looks good. And we can see here, due to the high resolution of distance to fault, that we have one cable, or the first connector is here. At 5 meters I can see the second connection, and at 10 meters I can very clearly see the third connection. And once again, all of these values are below 25 dB, so at this point it looks like we have a system that's performing very well. The final thing we're going to do is connect the actual antenna, or in this case our low PIM termination, to the end of the line and do final verification measurements. So we're going to go into measurements, return loss, and once again the return loss of the overall system now looks very good. So this is the measurement we're going to save as the final system measurement. So very quickly we've been able to, using the cable and antenna analyzer function of the PIM Master, verify that we have a site that's passing both the cable loss measurement, the distance to fault measurement, as well as the return loss measurement. The next step is now to proceed to PIM testing. I'm going to connect the system under test to the PIM test port, and here it is important that we apply the proper torque so that we maintain low PIM at the test port connection. We're now ready to proceed to performing our first PIM measurement of this system. We start the test and we see that we have a failure. If I was doing this test with a traditional PIM analyzer, the first thing I would do is start tapping on the connections, trying to find the location of that PIM source. As you can see here, I don't have any indication where it is. But with distance to PIM technology, with a single button push, we can now go into a mode that tells us the location of where the PIM problem is located. So with just a few seconds, we have an answer. And in this case, it's telling me that I see a high PIM peak at a distance of 4.91 meters. A new capability of the B Series PIM Master is that because we did our cable and antenna analyzer measurements on the same instrument, we can use those DTF measurements we did in cable and antenna analyzer mode to help us gain more information about the location of this PIM problem. So what I'm going to do is I'm going to hit Shift Trace. load a distance to fault trace, and we're going to go into the site 3456 directory that we were looking at. And the first one I'm going to load is the distance to fault measurement, where we had the open circuit at the end. And so what this tells me is that if I look at the location of where we know the end of the cable was and look at the location of our PIM fault, a delta marker has been set up and it tells us that it's minus 5.13 meters. So more information about the location of this PIM. We know that it's 5 meters closer to the instrument than the end of the cable. In a closed antenna system, or a system where we think the PIM source is internal to the system, a more useful trace to load is the distance to fault trace where we had the precision load at the end of the cable. So here we use, once again, the high resolution of the cable and antenna analyzer mode and see a very clear picture showing us exactly where each connector is. And here we can see the input connector to the system, that connector at 5 meters, and the connector at the end. And without even caring what the numbers are at the top, we know that that connection at the middle is where our PIM problem is located. So the next step is to perform our PIM repair. The repair in this case means removing the PIM standard from the system. So now that I've completed my PIM repair, I do my final PIM versus time measurement while tapping on the connections. We now see that we have a stable PIM measurement even when applying the dynamic testing. This is now a passing result. So now we've finished testing this site. We have not only a site that's passing from a return loss standpoint, but we also have a site that's passing from a PIM standpoint. And we've been able to do that using only one instrument instead of carrying two separate instruments to the site to perform these tests.